All right, in question 5, we're looking for a mechanism for the reaction given below. And this is an addition to an alkene, and specifically it's an addition to an alkene using NBS and UV light. And those reagents should immediately lead us to the conclusion that this is a different reaction than what we're used to with bromination. Anytime we see UV light, what are we typically looking at? Well, UV light in general leads to radical type reactions. And so that means a couple of things for the alkene. So it means that we're adding a bromine still, but what changes here, most importantly, is the fact that the alkene itself will still be present. So NBS is this compound, which has the weak nitrogen-bromine bond, and with the addition of UV light, that bond breaks to give us a bromine radical. That bromine radical can then remove a hydrogen atom from our alkene, and it's going to do so to form the most stable alkene. And recall, with radical formation, it's very much like carbocation formation. More substituted radicals are more stable, and anything that can help with resonance, such as being next to an alkene. So there's two positions that are next to an alkene, which are the two drawn here. But the one I drew in first, this one on the left, is also more substituted. So that bromine will remove that hydrogen and form an alkyl radical, which in this case we could more specifically say is an allylic radical because it's next to an alkene. So finally here, in this step we formed HBr. And that HBr can react with another molecule of NBS to form bromine. And then the bromine that we just formed will react with the radical that we formed in the previous step to successfully brominate the alkene next to the alkene.